All right, so we're going to finish up section 13.3 here. And let's see, a couple things to mention before we start this next thing. Note this little formula right here, that's always true, that if you have so alpha, beta, and this right here is gamma, those are the angles that that each axis makes with a vector. So like if you imagine this is the x-axis and this is the vector, the angle that you're rising up to meet the vector from the axis, that's alpha. And then same thing with the y and the z-axis and so forth. All right, so that little formula should always work out. And then secondly, this. When somebody mentions the I vector, I, remember, is a unit vector in the direction of the x-axis. So that would be 1, 0, 0. J, because we're in 3 dimensions now, would be 0, 1, 0. And then K would be 0, 0, 1. Now, if anybody asks you for the magnitude, like the magnitude of vector I, remember that would just be 1, because it's 1 unit long, it's going in the x direction. And same thing for J and K, the magnitudes are all 1. All right. So these direction angles, how to find these direction angles. So if you want to find the angle that your vector makes with the x-axis, you have your formula here. You have the dot product of the two vectors. You have the x vector and you have that vector. So we're just using the formula that we did on the last page up here to like do the same thing we did earlier. All right, so you're dot producting the two things, and not dot producting, but it's probably not a word. But anyway, you're doing the dot product of the two vectors, and then you are doing their magnitudes multiplied on the bottom. So this slide should not have a little 1 right here. So anyway, all right, so when you dot product a vector with this I vector, hopefully you realize that you are just getting the first number, because you're going to have the x, y, z times 1, 0, 0. And so you're just going to get the x, because the other two are going to turn into zeros. So what you're going to get is you're going to get a1. Well, a1 is just going to be like the first part, like the x value of your vector, because so you're getting that on top. On the bottom, the magnitude of the actual vector a. So that's going to stay. But the magnitude of this guy, remember, is 1. So this is all we're going to need. So if we want the angle beta, we do the cosine of beta. We're basically just going to get my 3-piece vector multiplied by this guy, or dot product with that guy. And so just the middle one's going to stay. So I'm going to have a2, and again over the magnitude of a. And cosine of gamma is going to be a3 over a. And this gamma, it probably should be kind of more like that. It's like a weird symbol. It almost looks like a Y. It's kind of like long like that. But anyway, all right. So there's your 3 formulas. So notice also what can happen here if you need to, like in a different situation. So if I want to find A1, A2, and A3, notice they're sitting right here in my formula. If I wanted to, you realize I could just like bring this over here and bring that over there and bring that over there, right? So if I did that, I would have that A1, A2, and A3. This is just the magnitude of A times a cosine of alpha, and then magnitude of A times a cosine of beta, and magnitude of A times the cosine of gamma. All right. And then if I pull out the magnitude of A, I would have just cosine of alpha, cosine of beta, and cosine of gamma left over. All right, so this is all equal to vector A. So if I needed to, if I knew a unit vector for the direction I was going, if I take this A and divide it by the magnitude of A, producing a unit vector, I'd have cosine of alpha, cosine of beta, and cosine of gamma. So that's actually kind of neat. If somebody gives you, so what this is saying to you, if somebody gives you a 3-dimensional unit vector, so they give you a vector that has a magnitude of 1 and it's 3 dimensions, what you have sitting right here, so if I'm just going to make up numbers, but let's say I had like, 0.2, 0.4, and 0.1. I know that the magnitude of this is not 1, but pretend it was. But anyway, right here, if I wanted to find alpha, I have it like right here. The cosine of my angle between my x-axis and my vector is 0.2. So I could kind of backwards find out what alpha was, what the angle between the two was. And then same thing for this and same thing for that. Okay? So anyway, that's kind of interesting. All right, so we're going to find the direction angles like we did before, and then the second example also. All right, so find the direction angles or the direction cosines. So basically we got cosine of alpha equals, I would have -2 over the magnitude of this thing. So the magnitude would be 4 plus 1 plus 25, so it'd be square root of 30. All right, so alpha turns into 111.4. All right, cosine of beta would be 1 over radical 30. And the cosine of gamma would be 5 over radical 30. So gamma would turn out to be 24.1 degrees, and beta would turn out to be 79.5. Okay, now in this last one here, I haven't given you everything you needed. Notice I didn't tell you anything about gamma. So I told you alpha, beta, but no gamma. And so that's going to be a little bit of something to figure out. Also, you're told that you have a vector that's 5 units long. So we're basically going to be we're going to find a vector that's in this direction and it's 5 units long. So we're kind of going to be going back to like this idea right here. Okay? But since I did not tell you what gamma was, we're going to have to figure out what gamma is by solving this piece right here. So you know alpha, you know beta. Gamma is actually going to be two different things. It's two different possibilities because it could go up or down. And so you'll see in a second. So let's figure out the possibilities for gamma, and then we'll have the rest of our answer. So remember, I got cosine squared of 32 degrees plus the cosine squared of 100 degrees plus the cosine squared of gamma, which I don't know, has to equal 1. So I'm basically going to subtract these two things from 1. I'm going to have cosine squared of gamma equals a number. I'm going to find the cosine of gamma equals something, and then we'll figure out in our calculator. So let me go to my calculator. I already have that typed in there. So I did this earlier. So you see up top here, what the heck? All right. I typed in 1 minus the cosine squared of those things. I got 0.25. So this guy over here is 0.25. And then I did, oh crap. And so then I did the square root, and I got 0.5. And then I did inverse cosine, I got 60 degrees. So this is 0.5, and we rounded off, but basically gamma is 60 degrees. Okay, so remember, when I did the square root, this is really plus or minus. So that means that the cosine was 0.5 and the cosine was negative 0.5. So since I'm going up and down, that means I was either up 60 degrees or I was down 60 degrees. Okay, because the cosine was positive or negative. And remember your A, S, T, C cosine is yeah, sorry, that's not down. It's over here. Cosine is positive, it's negative over there. So that's 60 degrees up top. So basically that's 120. So 60 or 120 degrees. All right, let's stop myself for a second. All right, so here we go. So if I want to find my vector, I will call it vector v, how about? I got 5 cosine of 32 degrees. I have 5 cosine of 100 degrees. And I have 5 cosine of either 60 degrees or 120 degrees. Okay. All right, so this guy here, it gets me 4.24. The second one gets me negative 0.868. And 60 and 120, the cosine of those things are the same. It's just one's positive, one's negative. They're both 1/2 and positive 1/2 and negative 1/2. So this piece right here gets you plus or minus 2.5. All right, so since it was left open to you in the question, then the answer could be two different things. All right, so now we get, not that page, we get to here, something called projection. So I could explain in greater detail to you how this formula comes about. If you really and truly want me to, I could show you. I have a paper where it explains it all out. But for projection, you basically just have to know this. You're basically just going to have to write down this formula here, and then this other one is a scalar projection, this one up here, and just know how to work it. So I'm going to tell you a little bit, but in the end, if you know how to work the formula, when somebody asks you for the projection, you just do the formula. But here goes. So a projection vector. So you see this little red one right here is labeled the projection vector. When you have a vector, all right, sorry, somebody knocked on the door and I forget where I was. Anyway, the projection vector. So the projection vector is that red one right there. And basically you have to think of projection, the projection vector, as a shadow of B. So you have B going this direction, and you have this the shadow of B kind of falling on this yellow vector A, and it's important to realize that this piece right here is perpendicular to the direction of A right there. So if you were to have a vector B and break it down basically into its parts. So B is broken down into this and this, because those are the two components of B. And so what we're looking for is we're looking for this piece right here. That piece right there is basically the part of B that acts in the direction of A. So it's the part of B that acts in the direction of this yellow one right here. And so that's called the projection of B onto A. Okay, so when you see this wording right here, it is read the projection of B onto A. So it's like you're doing the projection of B onto this little one right there, onto A, okay, in the direction of A. All right, and then you also have something down below called the scalar projection. Scalar projection is basically just going to be the length of that red vector, whereas the projection of B onto A is going to be a full vector. So when you do the projection of B onto A, you're going to actually get a vector for an answer. When you do the scalar projection, which has the COMP, this part right here probably means component of B onto A, that's just going to get you the length of this vector right here. So let's go ahead and do the two formulas on the next page. This picture over here, that's just a picture where B is going the other direction. It's the same idea, but also realize this from both of these pictures. The projection of B onto A is simply a multiple of vector A. So do you notice in both cases, this red vector is traveling along A. It's going along A. So it's in the same direction as A. It is some kind of multiple of vector A. So we just have to figure out like what goes right there. And that's where I could like kind of explain it to you more. If you really want to, you can come to Source after school. I could show you if you care, but otherwise you can just trust this formula here. So what I was talking about, the length right there multiplied by A. So basically then you have these two magnitudes put together, which gets your magnitude squared. So this right here is the formula for projection. And up top, when somebody asks you for the scalar projection or the component of B onto A, it is this piece here. You can see it's basically just like the length. Okay, so let's try it down here. So given these two vectors, x and y, I'm going to do the two formulas. So if I just want, I'm going to do the projection first because that's, I don't know, I want to. Anyway, so this is read the projection of y onto x. So you can see if you look at the letters, I have to do x dot y. And the thing that you're going on to is what you use in more places. So y onto x means I put the x down here, I do the magnitude squared, and then I also put the x over here. Remember, this part is just like going to be a number, and then you're multiplying it by the vector x. All right, because it's the length of the thing in the direction of the x vector. All right, so x dot y. So I need 3 times 2, so 6 plus 3 plus negative 4. So 9 minus 4 is 5. So I got 5. And on the bottom, I have the magnitude of x, and I have to square it. So magnitude of x would be 9 plus 1 plus 1. So 11. So radical 11 squared would just be 11. And then I have vector x again, which is 3, 1, 1. So you could leave these apart, or you could basically just put, 15 over 11, 1 over 11, 1 over 11, and put your component form. Oh, wait, not 1 over 11, sorry, 5. Okay. All right, so up here, the component part. So basically, it's pretty similar to most of what you had right here. So you have x dot y again, so you got 5. On the bottom, we have the magnitude of x, and so that was square root of 11. So that's finished. So that's going to be the length of the projection vector. So if I asked you to find the projection vector and then asked you to find the length of this thing, this right here is actually the length of it. So you don't need to do that. All right, so the last little thing we have to do is work. So work, there's going to be two basic formulas that I have highlighted here. So this piece here, this yellow one, and then this yellow one. So when you talk about work, one use of projections occurs in physics when you calculate work. The work done by a constant force, F, moving an object through a distance d is usually W equals Fd. But this only applies when the force is directed along the line of motion of the object. So in this picture right here, you have somebody pulling a cart, and they're doing it 35 degrees. So, you know, because their hand is like kind of higher than the cart. And so this is not the case where you're doing the same line of motion. So if you had somebody down here, you know, and they were like pushing the cart, that is basically in the line of the motion of the cart that's moving in that direction along this line right here, along the surface. And so that would be like W equals F times D. All right. But in most cases, you have somebody pulling something. There's an angle to it. It's not in the line of direction of the travel. The force isn't in the same direction as the line of motion. All right, so if the force is acting in some other direction, like this wagon here, then the work done by the force is defined to be the product of the component of the force along D and the distance moved. So in our case right here, what we would do is we would have to know how much force we're using, the distance that we're going, and the angle that we're applying this force in. Okay, and this also comes from the formula, you know, earlier when we did this, cosine theta equals u dot v over the magnitudes multiplied together. So I hope you can kind of tell right here that if you move these two pieces up there, it kind of looks like this. And so that leads you to this other formula right here, where the work is also equal to the dot product, because, you know, everything goes together there. Okay. All right. So these are our two formulas that we can use. All right. So let's just do that in the last page here. So if you have a wagon, a distance of 100, and a constant force of 70, so we need our work. I have my my force times my distance. So I'm going to have my 70 times 100. And then cosine of 35 degrees. So from there, it's just a calculator problem. You get 5,734, and the units are newtons meter, newtons per meter there, or I'm sorry, Newton meters. And so you guys all know maybe from physics that is joules, if you want to say that. All right, and then the last one here, force is given by a vector 3, 4, 5 and moves a particle from one point P to point Q. Find the work done. So in this one, we have more of a situation we're going to do F dot D. But I need the direction vector. So I need to basically just find the vector from P to Q. So 4 minus 2 is 2, 6 minus 1 is 5, and 2 minus 0 is 2. All right, so I'm going to dot these two things. So 3 times 2, I get 6 plus, what is it, 20 plus 10. So I get 36 joules again. All right, and that is it. Just under 20 minutes, and I will see you in class. Remember, your homework is to have this done. Do not do these problems down here because we're going to work on them in class. So you're just finishing section 13.2 and you're doing your notes. And I'll see you in class. Bye-bye.